Let's talk about diagonalization. Under some circumstances, we want to express an n by n matrix A in the form A equals P, D, P inverse, where P is an invertible matrix and D is a diagonal matrix. Why? Why would we want to do that? This makes it easier to calculate powers of A. For example, let's say we want to calculate a to the 50th. There would be PD P inverse times PD P inverse, etc., 50 times. But notice, this P inverse cancels with this P inverse cancels with the P in the next term, etc. This P cancels with the P inverse in the previous term, and we're left with P, D, 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 50 times, D, P inverse. In other words, P, D to the 50th, P inverse. Well, that's great, but how are we going to calculate D to the 50th? It's actually not that difficult. Remember that D is a diagonal matrix, which means that if there are any non-zero entries, they have to be along the main diagonal. Everything below and above the main diagonal is 0. So if we have a diagonal matrix of this form, D1, 1, D2, 2, etc., are the entries along the diagonal, D to the k is going to be D1, 1 to the k, D2, 2 to the k, etc. These are going to be the entries along the diagonal, and everything below and above the diagonal is still going to be 0. We call this factorization A equals P, D, P inverse, the diagonalization of A, and we say that A is diagonalizable. More generally, A to the n equals P times D to the n times P inverse. Let A equal this matrix. Can we diagonalize A? First, we find the eigenvalues and their corresponding eigenvectors. Why? The eigenvectors have to be linearly independent. An n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, the characteristic of polynomial is going to be negative lambda minus 1 squared times lambda minus 2. Don't verify that it just is. So the eigenvalues of A are going to be lambda equals 1 with multiplicity 2 and lambda equals 2. The corresponding eigenvectors, again, it just turns out this way, you don't need to check it, are going to be 1, 1, 0, 1, 0, 1 for lambda equals 1, and negative 3, 1 for lambda equals 2. The set of eigenvectors is linearly independent. So if you look at this set of 3 eigenvectors, that set of 3 vectors is a linearly independent set. How would you check this? We know how. Use the invertible matrix theorem. This set of eigenvectors is linearly independent because when you convert those into the columns of a determinant, the determinant is non-zero. And again, the invertible matrix theorem, that monster theorem that has many statements, A is invertible if and only if the determinant is non-zero, and that's also true if the columns of the matrix are linearly independent. In this case, the columns of the matrix are these 3 vectors, so these 3 vectors must be linearly independent. The set of 3 eigenvectors is linearly independent, thus we can diagonalize A. Well, that's what we'll do. Let's diagonalize A. The entries along the diagonal of D are the eigenvalues, so in this case that's 1, 1, 2. And the columns of P are the corresponding eigenvectors. So this is the eigenvector for 1. This is the other eigenvector for 1, and this would be the eigenvector for 2. The order of the eigenvalues is arbitrary. So if we wanted to, we could have stuck 2 up here. We could have stuck 2 up there and make this 1 and make this 1. So the order of the eigenvalues is arbitrary, but once their order has been chosen, then the eigenvalues, or the eigenvectors, have to be in that same order. So in other words, if we did put the eigenvalue 2 up there, then this eigenvector corresponding to lambda equals 2, well, we'd have to make that in the first column. Let's try. Let's see if it works. So PD P inverse looks like this. Here's our matrix P. It consists of the eigenvectors for the matrix, and D, it's a diagonal matrix whose entries along the main diagonal are the eigenvalues. And then this is just going to be P inverse. When you multiply P times D times P inverse, you actually get A. So it really all works out. And the converse is true. A equals P, D, P inverse, where P is an invertible matrix and D is a diagonal matrix, if and only if the entries along the diagonal of D are the eigenvalues, and the columns of P are the corresponding eigenvectors. Compute a to the 10th using the diagonalization of A. Again, this is where diagonalization comes in handy. Well, a to the 10th is P, d to the 10th, P inverse, as we saw earlier. This is our matrix P. This is d to the 10th, and here we have P inverse. D to the 10th, again, is going to be 1 to the 10th, 1 to the 10th, 2 to the 10th. Those are the entries along the diagonal, and everything else is 0. So that turns out to be 1, 1, 10, 24. That's what d to the 10th turns out to be. Multiply that by P, and then P inverse on the right, and this is what we end up with. And if you check this, you will find that this hairy matrix above is indeed a to the 10th. Let B equal this matrix with characteristic polynomial determinant of B minus lambda I equals negative lambda minus 1 times lambda plus 2 squared. Find the eigenvalues. Well, we know what those are going to be. I mean, here we have lambda equals 1. Here we have lambda equals negative 2. It has multiplicity 2, so we know those are the eigenvalues. We can see that from the characteristic polynomial. The corresponding eigenvectors, just trust me, it works out that way, are 1, negative 1, 1 for lambda equals 1, and negative 1, 1, 0 for lambda equals negative 2. Is B diagonalizable? No. Recall that an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. This set of eigenvectors is indeed linearly independent. You got two vectors, one's not a multiple of the other, so it's linearly independent. But there are only two eigenvectors for the 3 by 3 matrix B, so we cannot diagonalize B, because an n by n matrix has to have n linearly independent eigenvectors. We have a 3 by 3 matrix, and we have only 2 linearly independent eigenvectors. If the n by n matrix A has n distinct eigenvalues, then it's diagonalizable. The converse is not necessarily true. A matrix can be diagonalizable and have eigenvalues that are not distinct. We saw this in an earlier example. This matrix A is diagonalizable and has 1, 1, 2 as its eigenvalues. So it's diagonalizable, but it doesn't have distinct eigenvalues. It has 3 eigenvalues, but 1 is repeated. And lastly, there's no connection between invertibility and diagonalizability. An invertible matrix can be diagonalizable or not diagonalizable. A non-invertible matrix, that is a singular matrix, that's sometimes what we call it, can be diagonalizable or not diagonalizable.